Hello everyone, this is our last tutorial, electromagnetic waves. I don't want to go over every question in a tutorial, but I want to point on certain tricky questions here. So I'm going to use PDF of the file and I'm going to just tell a couple of words about every question or some interesting questions. Well, guys, what you see is a picture of electromagnetic wave. This electromagnetic wave is polarized horizontally. You see electric field has horizontal polarization. And the axes are a little bit like different from normal position what we have, right? Usually we have Z axis up and over here is Y and over here is X. Well, I don't know the reason, but they decided to set it like this. Maybe because they wanted to keep a variable as X, right? Now we do have two equations over here, equation for electric field and equation for magnetic field. Let me just choose color. Uh, so magnetic field is drawn only along x-axis. But if you look at the variables of magnetic field, you see there are just two variables, x and t. What does it mean? Means that all y's and z's are going to have the very same values for a certain x and a certain t. For example, you see point 1, it has a certain, well, let's consider point 4 actually. 1 is a little bit off the vector which is drawn over here. You see point 4 over here, that it has magnetic field vector going up along y-axis and electric field vector going horizontal along z-axis, right? So these two vectors are sitting at point x, like, I don't know, like whatever x coordinate is, right, of this point. Now, what is going to happen if I change for this point the coordinates y equals 0 and z equals 0, right, for this specific point. But what is going to happen if I change y and x, if I move somewhere like this direction or up? Well, nothing. Actually, it's going to be the very same set of vectors. I'm going to draw what is going to happen at point 3, and there are more points which you will need to answer yourself. So at point 3, electric field vector is going to be exactly same as this one, which is a little one over here, right? And magnetic field vector is going to be exactly same as this one. So that's going to be E and that's going to be B. What is going to happen if I move up from the point 4? If I move over here, for example, how the fields are going to look? Exactly same way. So magnetic field is going to be along y-axis, and electric field is going to be parallel to z-axis. So I'm going to kind of label it. Why does it happen? Because this is plane wave. Plane wave has only one coordinate changing, x coordinate, and time. So it's like so x and y and z coordinates are not affecting the magnitude of the field. So if you move in the plane YZ or parallel to the plane YZ, nothing is going to change. So if you move along any point over the plane which goes through a certain point, for example, over here, point where everything is 0. So all the points in this plane are going to have electric and magnetic fields equal to 0. But it's going to happen only at moment time t equals t0 at which they made this snapshot. And if t changes, the wave is going to move. And of course, in this plane, we are going to have different values of electric and magnetic field. Okay, so that's the first question I wanted to discuss. Actually, it's going to be applied over here to answer the questions. Also, it's going to be applied on the second page where they are moving in actually z direction. Here they're moving in z direction, and on the next page they're moving in y direction. Another question I want to kind of point out that they're asking in which direction the wave is kind of moving. And well, naturally for us think that it's moving in positive direction of x-axis. Like they did draw it like this, and it looks like it's going to continue in positive direction of x-axis. How to actually find out in which direction it's moving? Usually, guys, we are going to look at argument of sine. Imagine that we are looking at this point. At this point, sine has maximum, right? That's a maximum amplitude, right? So the argument at this point equals, for example, pi over 2. Why pi over 2? Because maximum of sine is happen at pi over 2 and equals to 1, right? So I'm going to write it down that kx plus omega t equals pi over 2. Now, what is going to happen if t is increasing? Like normally time is increasing, right? If this one increase, to keep this constant, x must decrease. What does it mean? What means that x is decreasing here? X was here, now it's decreasing. So x is going to move actually in this direction. And next moment of time, the maximum, this maximum is going to be actually over here. So what we see from this, that wave is actually moving in negative x direction, the direction of the motion. Okay, just like to explain it, because not obvious from the first sight, and maybe you guys don't know about this. Also, guys, I want to write down a couple of formulas. So we remember that the period of the wave, the time, kind of how fast the vector is going to change in time, like how fast it's going to change from the maximum position to 0 and then going down and go back, like one period in time. At this point x, it's going to oscillate, right? It's going to be maximum position for vector b, and then eventually it's going to be smaller, 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 eventually it's going to be 0, and then it starts moving in opposite direction until it reaches maximum and goes back. Oscillations like a sine, right? So we remember started writing it wrong, to calculate the period of periodic function, any like for sine or cosine, the period is 2 pi over omega, where omega is a coefficient of t. We also have some kind of period in space. So this is time period. Period in space is going to be lambda. And it's going to have a same formula, just going to be 2 pi over k. My pi does not look very nice. I'm going to raise my pi and draw it one more time better. 2 pi over k. So it's going to be space period. What is space period? It's how long is the wave in x direction. One period is going to be, for example, from this point to this point. So this is going to be lambda, one period. Well, you can make like period between two similar points. It's not necessarily supposed to be 0 points. Okay, so again, time period shows how fast this vector will go to 0 and turn into like negative direction of y-axis and go back. This vector b, for example, is going to oscillate, right? Making bigger and smaller. For us, it's going to look like the wave is moving, right? Because when it's making smaller, the wave is going to move like that direction, negative direction of y-axis. Okay, so we discussed these two questions. Now, one more question to discuss. So these two questions are going to help you to answer like what the questions about magnetic field, electric field. Also, you see they are labeling like with crosses different points in a plane perpendicular to YZ. You remember what I just said, that in the plane parallel to YZ, I said perpendicular, sorry, perpendicular to x-axis, but parallel to the plane YZ. All the vectors of magnetic and electric field are going to be absolutely same for all the points in the same plane, because the only variable here is x. So if you change x, something is changing. If you don't change x, nothing is changing. Well, unless you change time. Okay, so you can answer these questions. Over here, they're asking you about wavelength. Actually, in this question, you just look at the time period. Wavelength is going to mean the color of the wave, of the color of the light, actually. So we know that blue is describing shorter wavelength and red is describing longer wavelength. Maybe kind of going to help to answer the questions here. Now, guys, about the wire. Couple of questions about the wire and detecting of electromagnetic waves. Well, not very kind of obvious. They draw wire vertically, right? But actually in a description, they tell us that the wire is placed along, I think, z-axis. I don't know where it's written, but it's somewhere like is written. Yeah, suppose that the wire is oriented along z-axis. Well, means that actually, if you draw the plane which was on the previous page, if this is x and this is z and this is y, this wire actually is oriented along z-axis. So that's going to be the wire. Not very clear if you don't read carefully the manual, right? So wire is going to be like this. Well, if the wire looks like this, which field is going to be along the wire? If you go on the previous page, you are going to see that along the wire is going to be, well, I'm going to go to the very, very first picture, electric field, right? Electric field goes along z-axis. So electric field is going to be along the wire. I'm going to label it so electric field. Well, a little clue. What electric field makes with charged particles? Imagine that you do have some positively charged particles here, like I'm going to draw the little tiny circle over here, positive charge. Okay. Somehow I stopped drawing. Give me a second, guys. Positively charged particles. Well, we remember that electric force is electric field multiplied by the charge, right? And magnetic force, it's a charge velocity cross product with the field B. Well, because electrons or like positive particles in the wire are like at rest, electric field is going to start moving them just because there is a force applied to the electrons. And when the force is applied, you can just calculate it, multiply this electric field by the charge of the particle, find the force. If the force is applied, particles start moving with acceleration, right? Because we remember that when the force is applied, something is moving with acceleration. Talking about B vector, how B vector is going to look over here. Well, if you draw electric field like this, if you draw this wire vertical electric field like this, magnetic field is going to look like this. That's going to be magnetic field. Magnetic field is going to apply some force to electrons too, but this force is not going to kind of move them, right? Just why does it happen? Well, just remember that the velocity of electrons is going to be along the wire. The field is like this, and if you kind of multiply them, the force is not going to move it along the wire. It's going to move it perpendicular. Well, that's a little clue on how to like answer the questions. I think you can answer questions 1, 2, 3, maybe on your own. And here for the question, they're asking us, like, which way is going to be the best to orient the antenna? Well, that's going to be the best way to orient the antenna. If your electric field is directed horizontally, the best way to orient the wire to catch this field is going to be horizontal way. I want to say that TV radio waves and FM radio waves are oriented horizontally, so they are horizontally polarized. And you probably have seen old TV antennas, not new TV antennas, which are like just dishes, but old TV antennas are looking like a bunch of parallel sticks. And they are antennas like this. And you probably remember that they are horizontal sticks, right? Okay, so we discuss this and this. Now, for page 4, maybe it's going to look a little bit weird to you that they are writing down Faraday's law in terms of integral, right? What is this? A little line integral over here. People who remember calculus, that's actually work of electric field along the line, along the circle or loop. Okay, so if you have something like this, the wire bent like a rectangle, the electric field is going to work along this wire. And if you have changing magnetic field flux, well, actually this flux is going to create this electric field. And we are going to, normally in Faraday's law, we call it electromotive force, right? EMF. But for equations, they don't use EMF, they use integral actually. EMF, it's like the work which is done on the particles, thankfully to this change of the flux. Okay, so now they're asking you to evaluate actually this integral along the path from points 1, 2, 3, 4, 1 back. I'm going to go back and show you actually where this path is drawn. The path is over here. So this is 1, 2, 2, 3, 4. So we're trying to evaluate electric field. Remember that electric field, if it's perpendicular to the motion, to the path, to the displacement, is going to do no work, right? So the only work is going to be done from 1 to 2 and from 3 to 4. And remember that when something is moving object along the displacement, it's going to be positive work and negative from work. Here you see that positive is greater than negative just because the vector is greater. Okay, now they're asking us to calculate the flux of magnetic field. I'm sorry that I'm moving it so fast, but there is a best way for me to kind of point it. So after you evaluate this integral, you don't need to find actual number value, just need to say whether it's positive or negative, right? Now they're asking us to evaluate the flux or change of the flux quantity d, quantity d, d phi over dt with minus, what it's going to give us. Well, let's go back over here. So if we point area vector, well, I'm going to maybe like draw area vector over here, so you can, somehow my computer is not cooperating with me. Stop drawing things. Okay, I don't know what happened. Give me a second, guys. I'll fix it and then continue. Yeah, I fixed it. So area vector, I think I just pressed something on my keyboard and it does stop recording. So if you place area vector up, they describe it on the page 4, like why it's up actually, because area vector, when you consider a certain area is connected to the path you go around this area, then magnetic field is going to have a positive flux through this region, right? You consider magnetic field like maybe this arrow and this arrow, like magnetic field is changing, not changing with time, but changing with space, but it's going to be positive. It goes the same way as area vector. What is going to happen a short moment after, because we need to know the change of the flux, right? Is it going to become bigger or smaller? Remember that wave is moving in the negative direction of x-axis. What does it mean? That this arrow is going to move over here, and the big arrow is going to move over here, and total flux is going to become smaller because just smaller arrows are going to go through this region, through this area. Well, what does it mean? The final flux is smaller than initial, means that the change of the flux is negative, because you take like number 3, for example, a smaller flux, and subtract number 5, a bigger flux, you get -2. If you put minus in front of it, you are going to get a positive number, right? Okay, I think that's all guidelines, and they are going to help you to answer the questions. If I'm going to put a couple of videos also, which are explaining the structure of electromagnetic wave. Please watch them too. Okay, and I think that's all I wanted to explain. So basically, we are trying to check Maxwell equations, that the flux through this surface and the work of electric field around the boundary of the surface are going to be connected into this equation. This is actually, well, if you kind of remember calculus a little bit, this is just one of the calculus integrals, right? And it's calculating flux through the surface. Okay, I think that's all. I'm sorry that it's taken so long when I start lecturing, so I'm trying to avoid them. Well, they're asking what is going to happen if you kind of have the same equation but kind of multiplied by z. I think that's going to be just basically same wave which you have over here, because they don't write it over here, or maybe yeah, they do write it that it's along z. This one is unit vector along z-axis, so we know that it's some kind of k, right? And along y-axis unit vector is j, but I don't know, they decided to put it z with cup and y with cup. Okay, that's all. Okay, if you have questions, well, you can email me and I'm going to finish this lecture.